Before I start, I'm going to do a couple of acknowledgments. And the first one, Ken already alluded to a little bit. The only reason I'm giving a talk on this subject was because Ken allowed me to participate in a project that was his idea. He was the one who developed and got the funding for it, had the vision for this project on the I-40 bridge almost 18 years ago now. And with that, it really had a profound impact on my career to be able to be a part of that. And you'll be interested to know, I was at a conference 2 weeks ago, and professors from Europe were still downloading the data from that I-40 bridge project from our website and presenting it at a conference 18 years later. So again, I think that attests to Ken's vision, and I'm really in debt to him. So thank you. And then the other thing I need to acknowledge, what you're going to see here is the work of a lot of people, not just me, and in particular, a lot of outstanding students that I get to work with through our collaborations with UCSD, as well as through a dynamic summer school that we run at Los Alamos. So I can't emphasize enough how much of the good stuff you're going to see here is due to the interactions of those students. Anything bad is probably more due to me here. So I'm going to get going. The title of the talk is Structural Health Monitoring, a Grand Challenge for Engineering in the 21st Century. And hopefully, that may be a little bit bold statement, but hopefully that'll come out here as we do the lecture. one of the difficulties with giving a lecture in engineering, particularly like this, to a broad audience is, engineering lectures tend to be a little bit dry, a little bit boring. So I tried to spice it up and add a little adult content here. And I'll give you a warning when it's going to come up. It's probably R-rated, but in case anybody wants to leave the room here, I'll give you a little announcement on that. So first, what is this whole idea of structural health monitoring? And really what we're trying to do is mimic the human sensing and processing system in built infrastructure. So things like our nerve system and obviously the processing capability of the brain, but replicate that in built infrastructure so that we can assess damage and hopefully assess that damage before it gets to critical levels. And why is this of interest? So I've shown the bridge up in the upper left here is one that collapsed in 1967. I believe it's in West Virginia, over a river between West Virginia and Pennsylvania. And as a result of that, Congress enacted mandatory bridge inspection requirements. And those are that every bridge has to be inspected, a visual inspection every 2 years, which is actually in New Mexico handled by the Civil Engineering Department here at New Mexico State. But since that inspection requirement has been in place, you see all these other bridge collapses that have occurred. Most of them result in loss of life. The one you're probably most familiar with is the I-35 bridge in Minneapolis. So all these bridges were undergoing a similar inspection program that had been mandated as a result of that 1967 bridge collapse. So clearly there's room for improvement over the visual inspection processes that are in place or that are the standard right now. And those issues aren't limited to civil engineering infrastructure. They occur with aerospace structures as well, a variety of different damage scenarios. As a result of this skin coming off of in-flight, an Aloha Airlines flight, the FAA set up a non-destructive evaluation center at Sandia National Laboratory. It's right above the rental car plaza there. That looks at all types of damage occurring in aircraft. They're doing a lot of work actually on the suspected cause of that TWA crash that you see in the bottom right. That's the reconstruction of the airplane after they've pulled all the pieces off of the ocean floor and put it back together again. They suspect faulty wiring had caused sparks that ignited the fuel tank and blew the plane up. So one last slide on motivation. So why are people doing this? Well, a big motivator for this is to move from time-based maintenance to condition-based maintenance. We want the structures to be able to tell us that they need maintenance. We don't want to just do it on a time interval. So the idea is kind of like in your car, where you could change the oil in your car every 3,000 miles, every 3 months. Or you could have sensors that tell us when a certain amount of debris has built up in the oil, when the viscosity is degraded, and change the oil when it actually needs to be changed, not just on a time-based interval. So I showed a picture in here. This is from inside a semiconductor manufacturing plant, where you see them monitoring a piece of rotating machinery. And it's a little bit hard to see, but if you look over the shoulder of this guy, they have 2 pieces of redundant rotating machinery for every piece that they actually use in that plant. And that points to the economics associated with the plant going down unexpectedly. The engineers there told us that they estimate it would cost that company $10 million an hour if that plant goes down unexpectedly. All right, and that's a huge economic incentive to be able to understand how all your equipment is running and make sure that you don't have any problems. The interesting part of this is the reason those engineers are actually monitoring that piece of equipment is not because they had some new technology that they're trying out. It's because the janitor was dusting it off and he felt it was hotter than the other pieces of equipment and told the engineers that they ought to look at that one. And sure enough, the bearings were going out in that piece of equipment. Another big motivator, and where a lot of the money is being pumped into this technology, is what we would call combat asset readiness. The idea that you want your military hardware out there fighting the war and not in the maintenance hangar. So an example here is a Predator unmanned aerial vehicle. You see these in the news quite a bit. They're used extensively over in Afghanistan. It was not designed as a combat vehicle. It was designed as a surveillance vehicle. The Hellfire missile you see on the bottom was added after the fact. And there's concerns about the loading on the structure. Right now, they discard the wings after 2,000 hours of flight. Okay, and I believe there's a lot of life left in those wings, and these are not disposable wings. These are a couple of $1 million for a set of wings for a Predator. And they'd like to be able to show that, but they don't have the ways of doing that right now. And then the last motivator here is manufacturers of large expenditure capital equipment want to start looking at other business models other than selling that equipment. And their other business models are to lease the equipment, but instead of a time-based lease, charge you by the amount of life you use up for that piece of equipment. So like with that great big mining truck over there, they can tell that the life of that truck is directly related to how well the mine operator keeps the road graded. In a time-based lease, he doesn't have a lot of motive to keep the road graded. But if he's having to pay for how much he's beating up the piece of equipment, then he starts to think a little bit more about having the road graded. So, so those are both business and you could technical motivation for a lot of this technology. So what do we mean by damage? So in this case, we're talking about changes to the geometric or material properties of a structure that are going to adversely affect its current or future performance. And all materials in any engineered system have damage in them from the get-go, from the start. You can't build a material that doesn't have some initial flaws in it. And under the appropriate loading conditions and environmental conditions, those flaws are going to grow and coalesce to produce component level and then potentially system level failure. One of the real challenges for this technology is that we're having to monitor structures on widely varying length and time scales to be able to go from the damage that you see up at the material level to the system level failure you see in that aircraft. And that presents challenges for all types of scientific and technical endeavors. When we have to either model or measure on widely varying length and time scales, that's a challenge. So I thought just one slide here to think a little bit about how engineers and scientists study the whole concept of damage. And I think they do it by trying to answer 5 different questions. And they're not in any particular order here that I'm going to present them. But first of all, what causes damage? And material scientists will approach that problem quite differently than engineers approach the problem. So the engineers tend to think of, are we exceeding some allowable strength, deformation, or stability criteria? The material scientists are actually, what's happening down at that material grain boundary level that's causing the damage to initiate and propagate? What's happening during the manufacturing processes or assembly processes? We also ask the question, what can be done to prevent damage? So again, the material scientists look at that problem by saying, well, we're going to develop some new materials with different properties, maybe corrosion-resistant alloys. The engineers come up with design strategies and or limit how we operate the equipment. And then there's the question, is damage present? And this is where the structural health monitoring comes in, along with traditional non-destructive evaluation procedures. And the way we would distinguish structural health monitoring from non-destructive evaluation procedures, with non-destructive evaluation procedures, we're almost always taking the system out of service, and it's a very local inspection process. What we're trying to achieve with the structural health monitoring is much more autonomous and global monitoring of the system. We also might say, how fast is damage going to grow and reach a critical level once we have actually identified it? And again, that's part of the structural health monitoring process. But we also then start to couple that health monitoring process with a predictive capability that we would refer to as damage prognosis. And then finally, how do we mitigate the effects of damage? Well, again, we can change operational parameters. The most common thing is we do maintenance and repair of the structure. And the material scientists, a big thing right now is looking at self-healing materials. Materials that can, if a crack forms, can heal themselves back up again. Okay, so everybody in this room, I'm hoping, can look at these structures and say that they're damaged. All right, even the professors, without the help of their graduate students, can do that. All right. And it doesn't matter if it's an aircraft, an offshore oil platform, a ship, or a Hyatt Regency hotel down here. Everybody in the room can do that. And how'd you do that, though? You compared the pattern of that aircraft, offshore oil platform, ship, or hotel to the pattern of every good structure of those same classes you've seen in your everyday life, and said that that pattern looks like a significant outlier. Okay? You subconsciously employed pattern recognition to do this, okay? And it turns out that structural health monitoring, and in fact, all non-destructive evaluation are problems in pattern recognition, okay? You did it in a very qualitative manner, okay? What we're trying to do is do the same thing in a very quantifiable manner. And it turns out that if you embrace this idea of the problem being one in pattern recognition, it's going to open up a lot of other areas of technology that you can bring to bear on this problem. So, we think that the way you tackle this problem is through a four-step process. And the first step is operational evaluation. Can we just define the damage that we're trying to look for in as quantifiable a manner as possible? That would include things like the size of damage, the type, the location, the critical levels that we can't cross, and the environmental and operational conditions under which we're going to have to perform the monitoring. Then we're going to have to acquire some data from the structure. We're going to have to extract features from that data. It's very rare that we analyze the raw data coming off of the sensor. We usually extract some type of features from the data. And the idea is to extract features that are very well correlated with the damage that we're looking for. And then we're going to have some statistical models that allow us to say when the changes of those features are significant and indicative of damage. Because it's going to turn out with this data acquisition, there's a lot of things that can change the measurements that are not related to damage. And we have to separate out those changes from the ones that are related to damage. And inherent in those processes are these ideas of data cleansing, data normalization, data fusion, data compression, things that we tend to think of as technologies that people in computer science, information technology really deal with. Okay, so this is the process that we follow to try and tackle the structural health monitoring problem. Now the interesting thing is the people at Citicorp use that exact same process to look at credit card fraud detection. Okay, the people who regulate Medicare use that exact same process to look at how doctors are billing the government and make sure that there's no fraud in how they get their refunds for Medicare. That exact same process is used by Microsoft to do speech pattern recognition. Okay, and so this is the idea. Once you realize that this is a problem in pattern recognition, there's a lot of technologies from other areas, particularly machine learning, that are directly applicable to this problem. And the more you look at that other literature, you find that they have a lot of technologies that can really help you solve this problem. Okay, so I'm going to just talk a little bit about each of those 4 steps. The first, just this operational. I use a wind turbine as an example. It turns out there's a lot of work right now going on applications of structural health monitoring to wind turbines, both the blades, and this one is one that got struck by lightning, as well as to the gearboxes. But again, we want to come up, we're going to, in anything other than a research environment, we're going to have an economic or life safety justification for developing a structural health monitoring system. In the case of wind turbines, there's not much of a life safety issue unless you just happen to be below the wind turbine when it were to fall over. It's all driven by economics. And what I've just put up here is a few numbers about what their current annual maintenance budgets are and an overhaul budget. But all of this information starts to dictate what the cost of the structural health monitoring system can be. The definitions of damage to be detected, again, in these composite blades, it's delamination, and damage to the gearboxes is a big one and occurs more readily than actual damage to the blades. And then there's a lot of environmental and operational constraints. We're going to have to do the measurement on a rotating device. Okay, that poses problems. That might say we want a wireless sensing system that can be out on the wings. Turns out we don't want any wires on the blades because that makes the blade into a big lightning rod if we have wires out there. So there's a lot of constraints. It's going to be out, these systems have to stand wind, rain, lightning. A lot of wind turbines are being located offshore. I mentioned that we might want to use wireless sensing, but when those blades spin around, they generate electromagnetic fields that potentially interfere with wireless transmission. But these are all, if you will, getting as much information about the system design up front as we can to help us in the other portions of the process. So now we'll talk a little bit about the sensing part, and I would claim that all sensors, regardless of whether it's structural health monitoring or not, are deployed for one of 3 reasons. And the first one is detection and tracking problems. So like sonar arrays would be an example of that, sensors that are put out for chem, nuclear, or biohazards. And the structural health monitoring sensors really come under this detection and tracking problem. Other sensors are deployed for what I call model development, validation, and uncertainty quantification. So we might put out arrays of sensors to help us develop models for global climate modeling or traffic modeling. And the damage prognosis, again, this idea, once we've identified damage, of predicting the remaining life of the structure would come under this modeling aspect. And then control systems is the other one. So when we start thinking about the sensing systems for structural health monitoring, I'll make the statement that there's no such thing as a sensor that can measure damage. And I'll even make a stronger statement. There never will be a sensor that can measure damage. The sensors are going to measure the response of the structure to its operational and environmental loading. We have to take that data and transform it into information about the damage condition. And that's where that feature extraction and statistical modeling portions of the paradigm come in. But we can't do structural health monitoring without sensing. And it turns out there's a lot of different properties of the sensing system we have to think about. Some of the ones in red are the ones we're kind of actively working on right now. How we can harvest the ambient energy to power the sensor so we don't have to actually have a battery with the sensor. Active sensing, and by that we mean that we want the device that we put on the structure to actually pulse the structure with known waveforms. to enhance the damage detection process. Now, when we do it, we're showing it there at a very low frequency just so you can see the input capability. We're usually doing that much more like at 100 to 200 kilohertz, a very high frequency excitation. And we can't do the sensor development independent of how we're going to do the data interrogation part of the process if we really want to have a robust system. So again, this idea of coupling the sensor hardware with both the feature extraction and statistical modeling parts of the process. So right now, probably in every electrical engineering department in universities in the US, there's a lot of work on wireless sensor networks. And one of the applications for that is in the structural health monitoring area, where we have a sensor node, and within a sensor node is the sensor, some analog to digital converter, usually some local computing capability, telemetry, and most systems are battery powered right now. And the systems employ a reconfigurable hopping protocol to transmit data. And by that, we mean that the sensors send the data from one node to another to get it back to some base station. And they have the intelligence in there to realize that maybe if something happens to this node, then it'll hop maybe down here and back over. That's what we mean by reconfigurable hopping protocol. And that's done somewhat automatically in the sensor system. And it turns out, though, you don't get kind of uniform power consumption across your network. The nodes where more of the data is transferring through will lose their battery faster. We have a lot of redundant hardware, and in their current state right now, they have very limited processing capability. The processor is on board because from a power consumption standpoint, it is a lot cheaper to compute than it is to transmit data. So you want to do as much of your analysis of the data on the sensor node and only transmit results. And this is what one of the devices that our students have built looks like. You can see they're very small devices. It's about the size of a quarter, and we'll show a little bit more of these devices in a couple of slides. I think the really impressive thing here, that system has been built by a student. What you see there, the end product, is 9 months after that student started. He had never designed a circuit board before. He was a mechanical engineer, not an electrical engineer. And that's what he got to in 9 months. And that's really a testament to the mentoring that some of my colleagues do for these students. So this shows some of the work that we've done with these wireless sensor nodes. This is actually on a bridge about 10 miles north of Truth or Consequences, right adjacent to I-25, that the State Highway Department has made available as a test bed. This is a more complete version of that sensor node. And what you see with the helicopter up there is we're not embedding power with our node. We're using that helicopter to bring power to the node on demand. And it's transmitting RF energy through that antenna to the receiving antenna. The sensor node is up on the bridge. You can see the sensors themselves are that little white patch up here. It's on a washer, and we can monitor the preload of the bolt with that. We also have ground-based robots that can do kind of the same thing as the helicopter. So I'm going to show you a little video. This is not the adult content one, though. Keep waiting for that. And the first part of it is, hopefully if it's running, I tried this out before, it takes a second to get going. The first part is actually we have a strain sensing device on the bridge that just saves the largest strain through mechanical deformation that the device has seen and requires no power. And what we're doing is a back-to-back comparison of that with an electric resistance strain gauge. And you can see it gets the peak. It misses one peak. It can't quite reset fast enough, but then you see it just stores that largest strain. But now this is going to show the use of the helicopter, and it's sped up a little bit to show, just to get through the video a little bit fast. So what happened, this is the part of when you do stuff in a laboratory and you do it out in the field, things are a lot different. Because, so you see it flying up, this is, I don't know if it's going to be quite dark enough, but this is the voltage in the capacitor. That's how we store the energy that's being transmitted. And the blades really don't bend like that. That's a function of speeding up the photography. That's the receiving antenna. And again, the sensors are further up there. when they get the circuit set up, that when it gets to 3.8 volts, it has enough energy in the capacitor to take the readings. It broadcasts the readings back to this yellow box that has the product. But when we did this, it took about 30 seconds in the laboratory to charge up the capacitor. What we had no appreciation for is the amount of turbulence around the bridge. And it's a lot harder to hold the helicopter fixed. And what you'll see here in a second is once you see the data get up, you'll see a red line drop, and you'll see the preload measures come up from the volts that we have instrumented on that bridge. So I think it's just about there. There you go. And there's the so it dumped the energy, took the readings, and broadcast them back to the helicopter. Okay, so it turns out there's a lot to be done in the sensor arena. There's a lot of work going on, certainly on these wireless systems and a lot of other sensing technologies. I'm going to talk a little bit about the feature extraction part. So now, how do we take the data and transform it into information about the damage condition? Well, there's three ways we usually do that. We look at some kind of waveform comparison, which I've shown here and I'll talk about in a second. Sometimes we fit models to the data and look at parameters of the models and how they change if we fit to a subsequent set of data. And then also we might look at the residual errors of how well a model actually predicts the response of the system. But what we've shown here is just a real simple experiment. We had a beam with an accelerometer in the end. We lift it up and we pluck it and let it just vibrate. And here's the response. And what we've done here is a time frequency analysis. You can see the frequency as a function of time and the decay in the response that you'd expect as that beam dampens out over time. Okay, what you see on the other, we have a beam now that has a crack in it, and we do the same thing. And what you see is quite a bit different waveform that comes out, and you get harmonics of the fundamental frequency generated, which is a very standard feature of cracks opening and closing. Okay, and so we can use that to try and assess and apply, if you will, pattern recognition to those two waveforms as a way to quantify when the damage has occurred in the structure. This shows a concrete column that we pushed and pulled on. Actually, researchers at the University of California, Irvine did that. We just did some measurements on it. We had a shaker up in the top there, and we developed a statistical model using tools of statistical process control, things that they use to monitor manufacturing processes. And in the undamaged condition, these particular features that we're using, which are related to time series models, don't show very many outliers here, but when we have cracks forming in the concrete, we get all these outliers. It turns out these two bands are at the same width. It's just I had to plot them in a compressed form here to get all these outliers. And these are actually a very good way to do continuous monitoring of systems using these techniques from statistical process control. Okay, so now I wanted to talk a little bit, what are some of the real challenges for doing this? And if I wanted to point to the single biggest challenge for taking this technology from research to practice, it's this issue of environmental and operational variability. Again, when we put our sensors out there, there's a lot of things that can cause changes in those sensor readings that are not related to damage. And we have to separate those changes from the ones that are related. And so to get that concept across, this is that bridge just 10 miles north of Truth or Consequences. And we did a vibration test every 2 hours for a 24-hour period. And when I say every 2 hours, what that means is we had student labor, and while we were back sleeping, the students were out overnight doing the measurements for us. And you can see there's about a 5% change in the resonant frequency between day and night. It tracks very well with the temperature differential across the bridge. We actually put some temperature measuring devices out on the bridge. And so what you see in the upper right there is what the first mode looks like at 10 in the morning. It's skewed to one side. And when you look at the first mode at 5:30 in the afternoon, it's skewed to the other side. That's because the bridge is oriented in a north-south direction. The sun comes up and hits one side in the morning. It's the other side in the afternoon. If you said the top one was the pattern of your good structure and presented some pattern recognition algorithm with the bottom one, it would identify it as an outlier and potentially as a damaged condition if we didn't take into account the fact that we know there's this environmental causes of the change. So now, this is the next part, is the adult content part of the slide. And it's not what you might think of. It's more like a slasher movie than I guess what the other alternative for adult content is. So it's going to be a video of surgery. Okay, so if anybody doesn't like a video of surgery, hip replacement surgery. Okay, and again, it's the idea, I'm trying to get across this issue of variability. And we had a really interesting, we've been, in our summer school that we run, we've had an orthopedic surgeon suggest projects for our students for the last 5 years. And the nice thing is, he has a real sensitivity for engineers, because he was a civil engineer as an undergraduate, and now is an orthopedic surgeon. And one of their concerns when they put the femoral component into your femur for an artificial hip is in a not insignificant number of surgeries that shatter the femur. Because they're dealing with older people, a lot of times who have osteoporosis, very brittle bones. They have no way of knowing when that femoral component is fully seated in the hole that they've drilled out in your femur. And they do it all by feel right now. And what you're going to see in the surgery, they want to do what they call minimally invasive surgery, where the incision's only about that big. Okay? What you're going to see in the next slide that has the surgery is, first of all, how rough stuff this is. This guy isn't just tapping lightly. You know, he's really pounding on this thing. And look at how limited his vision is when he's doing this. So you see, he doesn't see a whole lot there. Now, watch him pounding. I hope I got this far enough that you're going to see him whacking on it. If I did this right, there should be a picture of him actually doing some of the... There. All right, so... Okay. I think that gets the point across. All right. So a really neat opportunity that our students had was that surgeon, well, not the one who was in the video, but the surgeon who's working with us. Because of our collaboration with UCSD, and UCSD has a big medical school, their medical school donated 10 cadavers to our students. And the surgeon volunteered his time to come and perform that hip surgery. What he'd asked us to develop is, could we put a sensor on the end of that femoral component when he's pounding it in and identify when that femoral component was fully seated in the femur. So I've whited out, just for identity purposes, the cadaver that's on the table. These are 3 students who were part of our summer school and the surgeon who's working with us. But right off the bat, you can see the different size femurs, femoral components that they have there. Okay, and then up in the top you see our instrumented femoral component as it's been inserted into the cadaver. But the real issue with this was, for the cadavers that we did, you can see the age of the people, their weight, their height. There's a lot of variability between the different people. And we could get this to work in the laboratory on artificial bones. Given good indicator, we could track a feature in the measured response data that gave us a good indication of when the femoral component was fully seated. But when we tried to extend that and do it with people that have all this variability associated with it, we couldn't get the procedure to generalize and account for all the variability between different individuals. So this is, again, a big challenge for this technology. Is this whole idea of variability that occurs even in the undamaged systems. And it turns out, so he took all of those to fracture. It actually turned out one of the cadavers actually had artificial hips in it. And we couldn't use that one. Okay, so what I've shown here, I'm going to show in this next slide, is a bunch of applications that we have worked on. And just to give an idea of the breadth of application of this technology, and this is certainly not an exhaustive list of all the things that people are looking at right now for structural health monitoring. But we've actually looked at doing the monitoring as we're manufacturing things and being able to actually correct for things like poor surface finish during manufacturing, as opposed to the standard right now is that you manufacture a part and then do post-manufacturing inspection. You've already seen the bridge structure. This just shows some of the sensors mounted on the girders underneath the Alamosa Canyon Bridge. We're actually asked to do some monitoring of roller coasters. And the issue here is that these polymer coatings on the roller coaster wheels come off on a regular basis, and they'd like to be able to identify that as soon as possible. We've done work at looking at corrosion and cracking in pipes. The bolted joints that you've already seen on the bridge, this was just a laboratory test of that. We've also looked at the next generation of Navy destroyer. The plans are that the above main deck portion is made out of composite materials, the below main deck part is made out of steel, and you have these composite to steel connections. And there's concern about creep in those connections and loss of preload in the joint. They also have a requirement that they want to reduce the crew size by 70% in this next generation of destroyers. So they can't just send somebody down to periodically tighten the bolts. They want to be able to actually monitor the bolts. We've worked with the people at UCSD. It turns out the Predator is actually fabricated very close to UCSD's campus, and we've worked with the people there to look at monitoring the wings of the structure. This is the artificial bones for that femoral component test. Composite materials that we've shot with projectiles and then looked at identifying the damage and delamination. Surface effects fast patrol boats that NATO has. Some large-scale scientific projects that we have at the lab. This Raptor telescope is used to observe gamma ray bursts. It has a polymer drive mechanism. So this telescope receives a signal from a satellite that detects a gamma ray burst and then automatically focuses on that gamma ray burst and takes pictures of it. And the drive mechanism periodically wears out. Again, these are supposed to be autonomous devices, but parts of the drive mechanism wear out. Some of our weapon systems. And most recently, we've been working with the Navy on an advanced ship design, these all aluminum hull ships that are actually a tri-hull design meant for very high-speed operations in coastal waters. But that gives you kind of a range of different types of applications that are being looked at. And again, this is certainly not an exhaustive list of the applications. Okay, so what I was going to do with the last few slides is just talk a little bit about some of the challenges. I've already mentioned the one about the variability, but there's also this need for long-term demonstrations for this technology. Everything that you've seen that we've done have been relatively short-term demonstrations. And those long-term demonstrations are expensive to do, so that's a challenge certainly. And I put up the second bullet, are we choosing the right applications? And I'll use the example of the two aircraft here that we might want to develop this technology for. So the Airbus 380, is this aircraft that holds about 600 people on board. And they are actually looking at this technology for commercial aircraft. But the deal is, if the system doesn't work, we have a real life safety issue with the Airbus 380. There's no life safety issue with the Predator. Okay, I mean, I guess you could say that Predator could crash, if damage occurred, it could crash into somebody, but I'd call that a second-order life safety issue. There's no first-order life safety, so that might be a better aerospace application to focus on. But the economic drivers for the 380 might be a lot larger than they are for the Predator. And then I also had this the need for real-world demonstrations, and in parentheses the catch-22, and this is the work that we did with Ken on the I-40 bridge. All right, so that's certainly getting out there trying to do it on a real-world structure. But in general, most owners of expensive structures are not going to put one of these systems on board unless you've been able to demonstrate that it's effective. But nobody's going to give you a structure to damage just so you can demonstrate that your technology is effective. And that's what I mean by the catch-22. That's the hard part of transitioning this stuff from research to practice. The time scales that damage evolves on are a real issue. So a lot of this monitoring we want to do for long-term degradation issues of structures. And so some of the things we have to deal with are just the continuity and the maintenance staff. So something like the Brooklyn Bridge, that's been out there a while. And some of the time scales that might be associated with the damage are longer than the careers of the maintenance engineers. Data archiving and retrieval is going to be a big issue. With very small sensing systems, you can generate phenomenal amounts of data. So right now, they have systems that the FAA has certified in rotorcraft called health and usage monitoring systems. They generate something like on the order of 40 gigabytes of data per hour of flight, okay? And that's a lot to manage, okay? Changing maintenance budgets, sensor technology, and how well that sensor technology is going to hold up. The electrical engineering component of this is probably the fastest evolving portion of the technology, the sensing technology. Then we have the other case, so that's for long-term degradation. Then we have the case where we want to make decisions about our structures after they've been exposed to extreme events. And those extreme events could be things like natural phenomena hazards, hurricanes, earthquakes, or man-made things like blast loading, or this A-10 aircraft that got shot up over Iraq and amazingly was able to land after being shot up that bad. But for those types of applications now, where the damage is occurring really fast, that's going to put a lot of pressure on the sensing and processing hardware. We're going to have to do that sensing and processing really fast. For cases maybe like with civil infrastructure, we've got to get our assessment to first responders. We have much more severe consequences a lot of times with misdiagnosis. And I think if we really want to be able to do stuff and have an impact on things like that A-10, we have to start thinking about coupling the health monitoring systems in with control systems. Because a lot of times the pilot isn't going to be able to react fast enough to compensate for that type of damage. Okay, and then in addition to some of these technical barriers, there's some non-technical barriers to the transition of this technology. So first of all, cost. As soon as you start getting into these multidisciplinary projects, you need more people, and that drives the cost up, okay? So since I'm at a university, I thought I'd throw out this one, tenure and promotion at US universities. And I said US because I've done this talk a lot in Europe and other countries, and I don't know if their system is the same as ours. But tenure process rewards the individual investigator. And I hope something that has come across in this talk is that there's no one individual investigator who has all the knowledge to tackle this problem. This is really multidisciplinary stuff. And we really have to have a mechanism that faculty are rewarded for participation in these multidisciplinary projects. But we have to temper that also with the idea that realistically, the graduate students who end up being the ones who do a lot of work on the development of this technology, they need focused topics still, though, for their dissertations and master's theses. So it's not an easy issue to deal with. Industry has very short time horizons with research in general. Regulatory agencies aren't involved in the technology development to much of an extent. I put government inefficiency. All branches of the military are actively pursuing this technology, along with places like the Department of Transportation, the Department of Homeland Security, but there is no coordinated effort. And a lot of the parts of this technology are transparent to the particular application, particularly the statistical modeling portions of the process. And then the last one is really more of a question to bring out, again, because I'm at a, I think we have to ask ourselves, is our education system evolving to address the needs for more multidisciplinary technology developers and integrators? So our universities are outstanding at training specialists, and probably particularly at the graduate school level, and they need to remain outstanding at training specialists. But we need to think about augmenting that training with more multidisciplinary programs. And in particular, the technology leaders of the future are going to have to be much more multidisciplinary than the technology leaders are today. Okay, and right now, I would say we don't have the programs to really train people in a more multidisciplinary mode. I in no way advocate that we change or stop doing what we're doing right now. We need to continue, like I said, to train the people in focused areas and have that. But we also need to have more multidisciplinary programs. And again, that's the way research is going to go, at least from my opinion. And then I put the last one. It's always an issue, and has been on several of the projects where we've tried to work with industry, is issues about litigation and intellectual property. I put this one up here not because I'm going to read it all off, but I put it up here to say that the reason, again, the talk was entitled A Grand Challenge Problem. And the reason I think it's a grand challenge problem is all these different disciplines have a role to play in the development of this technology and the transition of this technology from research to practice. So the multidisciplinary nature of this work is one of the key issues that, in my opinion, make it a grand challenge problem. And now the next one is just kind of, I've talked about in the structural health monitoring process, just the stuff that's essentially in that red ellipse there. But this is, the structural health monitoring is one component of a much bigger process. And the first step in that, expanding that process, is to take the information that we have from the structural health monitoring system and be able to predict the remaining life of the system. Okay, and to do that, we have to bring in predictive modeling capabilities to the process here. So that's the first step. But what we're really trying to do with the structural health monitoring and the damage prognosis is provide cradle-to-grave total system state awareness for our infrastructure. And that starts with trying to design system functionality in at the material and manufacturing level. Okay, and we want to minimize the use of raw materials, minimize scrap. You know, at Los Alamos, we manufacture things out of materials like high explosives and plutonium. You know, that's a really major issue to deal with any excess scrap that comes from those processes. We want to start building system intelligence in at the material level. And then we want to be able to monitor and assess the in-service condition. This is really where the structural health monitoring starts coming into play. We want to maximize service life and reliability, minimize maintenance, energy demands, and environmental impact. And then we want to do intelligent system retirement, okay? And again, this is where the damage prognosis comes in. Predict end of life, you know, again, maximize recyclable components, minimize hazardous non-recyclable components. And all these parts are feeding back into each other as we go through the process. But this is an end goal for engineering in the 21st century. And if you ask me, how do we realize that goal of cradle-to-grave system state awareness, we do it by building biomimetic functionality into our built infrastructure. Okay, and so I've just shown a whole bunch of different biological analogies to some of the different things that we're trying to put into infrastructure right now. So I showed you the example of actuation for the active sensing, which would be like the muscles. The sensors are clear. You can think of a circulatory system, part of the self-healing materials. They kind of mimic a circulatory system. But building that type of functionality into our infrastructure is how we're going to achieve this cradle-to-grave system state awareness. And so to do that, again, I think engineering has to be thought of not as mechanical engineering, electrical engineering, what have you. It has to be thought of integrating these areas of predictive modeling, advanced sensing technology, and information technology, really built on a firm understanding of materials behavior. And the way we develop predictive modeling then for a specific application will certainly be different. But this is the way that I think we really need to think about engineering in the future. So the last one is, last couple of, I just have 2 or 3 slides more, but what I'm showing here is, in a lot of these areas, the US is not the leader in this technology. Okay, this shows bridges that were having large-scale instrumentation systems placed on them before 2000 in China. Okay, and there's 5 bridges here, and some of those numbers, the total number of sensors over on the right, I know are dated, because the Singma Bridge has about 1,000 sensors on it right now. Before 2000, you couldn't have found any bridge in the United States outside of ones of California that have strong motion instrumentation for earthquakes on them, and those would be on the order of maybe 10 to 20 sensors mounted on. It was done in China. Okay, look at now some of those sensor counts that they're putting on these structures. Okay, there's nothing comparable to this in the United States right now. So in terms of, since 2005, all major bridges as well as older structures are getting instrumentation systems put on them. They're on the scales of 1,000 plus sensors in some cases on the bridge. They cost on the order of less than 1% of the construction cost for a new construction. Some of the systems have been out there for a while, but some are still relatively new. They have a lot of advanced sensing technology. There's nothing like this in the United States. I don't believe they really know what to do with the data they're getting from these systems right now, but they're getting the data. And they're going to learn what to do with it. And the United States runs the risk of buying this technology 10 years, 15 years down the line from China. Because we are not taking the proactive approach to developing this technology right now. Okay, so just to conclude, so hopefully what's come across here is this is really multidisciplinary technology development. You really have to integrate a lot of different areas of technology to be successful in this arena. And in the 3 big areas, again, are the sensing, data interrogation or information technology, and predictive modeling capabilities. The reason I titled it a grand challenge for the 21st century is not only that it requires all these different technologies, but there's a tremendous potential for economic and life safety advantages to be provided by this technology. However, it's hard to do multidisciplinary technology development, as we found in the Engineering Institute that we've done with UCSD. You really need people who are willing to act as technology integrators. If we try and the structural engineers try to talk to the computer scientists, sometimes we talk a tremendously different language. So there's a lot of issues. It's not easy stuff to do, but it is the future. And with that, I'm going to conclude the talk.